7,000 light-years from here, in the constellation Cygnus, a star is dying by inches, and nothing is sucking it in. Every second, a thread of blue-white gas peels away from its surface and arcs across empty space, curving slowly, almost gently, toward something you cannot see. It does not fall in a straight line. It does not vanish in an instant. It spirals patiently the way water spirals into a drain, gathering speed only at the very end. For over 60 years, people have called the thing waiting at the center of that spiral a monster, a vacuum, a mouth. It is none of those things. And by the end of this film, you will know exactly what it is actually doing to that star, and why the truth is stranger and far more elegant than the myth. This is Objects in the Dark, a quiet place for the true stories of things out there. If this is your first time here, consider staying a while. There is no shouting in this channel and no scientists being stunned. Just real objects and what is actually happening to them. Here is the promise. By the time we reach the end of this story, you will know precisely what a black hole does to the things near it, and it is not what you were taught to picture. You will also learn about a wager made in 1974 between two of the most careful scientists alive over whether this particular object was even real. That wager took 16 years to settle, and it ended with one of them breaking into the other's office while he was away. Stay for how it ended. It will change how you read everything that comes before it. Its name to astronomers is a string of letters and a number, Cygnus X-1, not a poetic name, a catalog entry, and that is fitting because for the first decade of its existence in human knowledge, nobody knew what it was. They only knew it was bright, in a part of the sky where nothing bright was supposed to be. The story begins in 1964 with a rocket. Not a satellite, not a space station, just a slim-sounding rocket called an aerobee, launched from a range in New Mexico, carrying instruments that could see a kind of light human eyes cannot, X-rays. Our atmosphere blocks X-rays from space almost completely, which is a mercy for anyone standing on the ground, but a problem for anyone trying to study the X-ray sky. So for a few minutes at a time, scientists would fire detectors above the atmosphere on the back of a rocket, let them stare upward, and then fall back to Earth with whatever they had caught. On one of those short flights, a detector caught something unexpected in the constellation Cygnus, the Swan. A source of X-rays, faint and strange, coming from a patch of sky that, to any ordinary telescope looking in visible light, appeared almost empty. They gave it a name built from where it was and the order it was found. Cygnus X-1, the first X-ray source charted in that constellation. For years, that was almost all anyone knew. A point of X-ray light with no obvious home. Then, in the early 1970s, a satellite named Uhuru, the first satellite built entirely to map the X-ray sky, began watching that patch of Cygnus continuously instead of in brief rocket glimpses. And it noticed something the earlier flights could not have caught. The X-rays were flickering, brightening and dimming in fractions of a second. That flicker mattered enormously. Anything that can change brightness that quickly cannot be large. A cloud of gas the size of a solar system cannot brighten and dim in a fraction of a second, because light itself would take longer than that just to cross it. Whatever was producing this light had to be small, compact, something close to the size of a city, not a star. Astronomers went looking for a visible companion in that same patch of sky, and they found one. A blue supergiant star, catalogued as HDE 226868, blazing hot and enormous, tens of times the mass of our Sun. It sat exactly where the X-rays seemed to originate. And when they measured its light carefully over days and weeks, they found it wobbling, its light shifting slightly toward blue, then slightly toward red, on a steady 5.5-day rhythm. A wobble like that has one honest explanation. The star is being pulled, rhythmically, by something orbiting it, something with real mass, tugging the star back and forth as they circle a shared center of gravity. You cannot see the thing doing the pulling. You can only see its fingerprints on the star that dances with it. So here is the ordinary world of this system, before anyone doubted what it meant. A brilliant blue supergiant, one of the hottest, most luminous kinds of star that exists, locked in a 5.5-day orbit with an invisible partner. The partner is dense enough and dark enough to leave no light of its own, only a gravitational signature and a stream of X-rays where matter meets it. Two objects bound together, spinning close in the dark, one of them blazing and visible, the other unseen and silent except for the faint scream of radiation at its edge. For the star, this arrangement is already a kind of slow erosion. Blue supergiants like HDE 226868 are not stable, quiet stars. They are furiously hot, and they shed material constantly into space in what astronomers call a stellar wind, a river of charged gas blowing outward from the surface, driven by the star's own radiation pressure. Under ordinary circumstances, that wind would simply drift away into the emptiness around the system and be lost. But this star does not have ordinary circumstances. It has a massive, compact neighbor sitting nearby, and that neighbor's gravity is enough to catch a portion of that outflowing wind before it can escape. Caught gas does not fall straight down like a stone dropped from a hand. Because the star and its dark partner are orbiting each other, the captured gas carries momentum sideways as well as inward, and that sideways motion means the gas cannot simply plunge in a straight line. It has nowhere to go but into a spiral, flattening over time into a thin, furious disk of gas swirling around the compact object, gas rubbing against gas, friction converting motion into heat, heat climbing, until the innermost edge of that disk reaches millions of degrees and glows brightly in X-rays. That disk of superheated, spiraling gas is the true source of the light the Aerobee rocket caught by accident in 1964. This was the setup, a star losing a little of itself with every orbit, feeding a hidden companion not through suction, but through gravity, geometry, and the simple stubbornness of angular momentum. It was, by any measure, already a remarkable discovery. The first strong X-ray source confirmed to be paired with a specific, ordinary-looking star. But identifying the companion star only sharpened a much harder question. What exactly was on the other end of that orbit? Something with mass, something compact, something dark. Astronomers had two serious guesses on the table, and only one of them was a black hole. By measuring the star's orbital wobble precisely enough, physicists could calculate a number called the mass function, a lower limit on how massive the unseen companion had to be, based purely on how hard it was tugging on the visible star. Through the 1970s, as those measurements were refined, the number kept climbing. Somewhere around 6 times the mass of our Sun, at minimum, was locked into that tiny, dark, X-ray bright point in space. That number mattered because there is a hard ceiling in physics for how massive a neutron star, the densest known object short of a black hole, can be. Neutron stars are the collapsed cores left behind after certain supernovae, matter crushed so tightly that a teaspoon of it would weigh about as much as a mountain. They are extraordinary. But even a neutron star has limits, held up against total collapse by the pressure of tightly packed particles resisting each other. Above roughly 2 to 3 times the mass of our Sun, that resistance fails, and there is no known force left in physics that can stop the collapse from continuing all the way down to a black hole. A companion with 6 or more solar masses was too heavy to be a neutron star, and too dark and compact to be anything else astronomers had ever confirmed. Every ordinary explanation had been tested and had failed. What remained was the extraordinary one, and extraordinary claims, especially in physics, are supposed to survive extraordinary scrutiny before anyone accepts them as fact. This is where the story turns, because not every physicist was ready to accept it, and one of the physicists who hesitated the longest was the one you might least expect: Stephen Hawking, the same scientist whose own theoretical work on black holes had helped make them a serious, mainstream subject of study in the first place. In 1974, Hawking made a wager with fellow physicist Kip Thorne. Hawking bet that Cygnus X-1 was not a black hole. Thorne bet that it was. The prize on both sides was a modest magazine subscription, hardly the point. The real reason Hawking made the bet, by his own account, was not genuine doubt. It was insurance. He had spent years of his career building the theoretical case for black holes. If it turned out, against all the mounting evidence, that Cygnus X-1 was something else entirely, he wanted to have at least one something on the way down. For 16 years, the bet sat unresolved, not because anyone seriously expected a different answer, but because proving something in astrophysics beyond reasonable doubt takes patience that no headline ever wants to wait for. Telescopes improved. Measurements of the star's mass, its distance, its orbit, were refined again and again, each new dataset tightening the case, narrowing the range of what the invisible companion could possibly be, until the alternatives were no longer just unlikely. They were essentially closed off. By 1990, the evidence had become, in Thorne's own words, overwhelming, and Stephen Hawking, true to the wager and famously fond of a good final gesture, chose not to wait for a quiet, polite handover. While Kip Thorne was away traveling, Hawking had himself brought to Thorne's office at Caltech, and there, without his colleague present to watch, he broke in and signed the concession himself, on the document they had drawn up 16 years earlier. Cygnus X-1, after 16 years of caution, was declared, by the very people arguing over it, to be exactly what the data had been saying all along: a black hole. That is where most tellings of this story end, with the bet, the concession, the tidy resolution. But the resolution of the argument is not the most important thing this object has to teach you. The most important thing is what it reveals about what a black hole actually does, once you strip away 60 years of the wrong picture. Here is the myth stated plainly so we can take it apart. A black hole is not a mouth. It does not reach out. It does not pull harder at a distance than any other object of the same mass would pull. If you could somehow remove our sun this instant and replace it with a black hole carrying the exact same mass, Earth would not be sucked in. Earth would not even notice, gravitationally. It would continue circling that spot in space on the exact same orbit it follows now, at the exact same distance, for the exact same reason it always has, because gravity depends on mass and distance and nothing else. The only difference you would see, eventually, is that the sky would go dark, because the thing at the center would no longer be shining. What is actually happening to the blue supergiant orbiting Cygnus X-1 is not an exception to that rule. It is a demonstration of it. The compact object at the center of that system pulls on its companion with exactly the gravity its mass allows, no more, the same as any star of 20 times the sun's mass would. The star is not being devoured by something reaching across space to grab it. It is losing material the way stars losing material always do, through its own outward wind, and a nearby massive object is simply catching a share of that wind the same way any sufficiently massive neighbor would. The strangeness, the genuine, well-earned strangeness of a black hole, is not in how it pulls from a distance. It is in what happens to matter that gets close enough to cross a boundary called the event horizon, the point past which not even light can climb back out. Far from that boundary, a black hole behaves exactly like any other mass in the universe. Only very near it does the picture become something nothing else in nature can produce. Space and time themselves bending so sharply that falling forward becomes as unavoidable as falling in time is for the rest of us. That is the true edge of the strangeness, not a distant vacuum cleaner. A local, extreme rewriting of the rules, confined entirely to a region smaller than most cities, wrapped around something with the mass of 20 suns. Everything dramatic you have ever seen in the disk around Cygnus X-1, the millions of degrees, the X-rays bright enough to be caught by accident on a rocket in 1964, comes from ordinary physics pushed to an extraordinary edge. Gas falls inward because it has nowhere else to go once its orbit tightens past a certain point, not because something is reaching out to seize it. Friction between spiraling layers of gas converts orbital motion into heat, the same way rubbing your hands together converts motion into warmth, just at a scale and temperature that has no equivalent anywhere on Earth. The light we detect is not the black hole shining. It is the last light of matter that has not yet crossed the boundary, radiating everything it has, right before it goes dark for good. So the honest answer to what a black hole does is this. From far away, it does exactly what gravity has always done, holding orbits steady the same way the sun holds ours. Up close, in the very last stretch before the horizon, it does something no other object can do, and physicists are still working out the finer details of exactly what that looks like from the inside, because no signal has ever come back out to tell us. That last part is not a failure of the story. It is the honest ending of it. We know, with 16 years of hard-won certainty, that Cygnus X-1 is a black hole. We know, with a century of tested physics, exactly how it behaves from any reasonable distance. And we still do not fully know what the inside of that horizon actually contains, because nothing that crosses it has ever been able to send word back. That is not mysticism. That is simply the honest edge of current knowledge, and it happens to sit right there, 7,000 light-years away, wrapped in a disk of dying starlight. Right now, while you listen to this, gravity is holding you against whatever you are sitting on, pulling you down with exactly the force your mass and the Earth's mass require, no more and no less. It is not sucking you into the floor. It is simply doing, at ordinary scale, precisely what a black hole does at an extraordinary one, obeying the same single rule everywhere all the time, whether the object producing it is a planet, a star, or something so compact it lets no light escape. Most people go their whole lives picturing black holes as mouths in space, waiting to swallow whatever drifts too close. You know better now. And the next time you hear someone call one a vacuum cleaner, you will know exactly what to say, and exactly which 16-year-old bet finally settled the argument. Which part of this story surprised you the most? The bet, the rocket, or the myth? Tell me in the comments. I read every one. I will see you in the next one.